Find the volume of a solid generated by rotating the region bounded by y equals the square root of x, y equals 0, y equals x minus 2 about the x-axis. The first thing when we find the volume of the solid generated by a rotation is to draw the region, the bounded region, using the given curves. First, we were given y equals the square root of x. The line y equals 0 is the x-axis. The line y equals x minus 2 is a line that goes through y equals negative 2. Observe that the enclosed region is only this shaded region above the x-axis, not the region that touches the y-axis. The intersection of y equals the square root of x and the line y equals x minus 2 needs to be determined. To do that, we set the two equations equal to each other. X minus 2 equals the square root of x, and we solved for x. Square both sides of the equation. We have x minus 2, the quantity squared, equals the square root of x squared. This is x squared minus 4x plus 4 equals x. This will give us x squared minus 5x plus 4 equals 0. So we factor this at x minus 4 times x minus 1. We have x equals 1 and x equals 4. When x equals 1, y is 1 minus 2, which is negative 1, so x equals 1 is not the solution because y needs to be positive. Y equals the square root of x. And so the intersection is at x equals 4. If we set y equals 0 equals y equals x minus 2, we will also see that the intersection is at 2. This enclosed region is being rotated about the x-axis. If we use the Washer method, then we would need to divide it into two integrals. And so we will use the Shell method. To use the Shell method, we will slice the cross-section parallel to the axis of rotation. We obtain a representative shell. This shell has a thickness of delta y. The radius of this shell is the distance from the axis of rotation, which is the x-axis, to the point where we slice the cross-section. And this is the vertical distance, so that the radius is y. The height of the shell is the horizontal distance, but this horizontal distance is the difference between the two curves. To find the height of this shell, because it is a horizontal distance, we will take the x on the right minus x on the left. And so we would need to express the function in terms of y. If y equals x minus 2, then x equals y plus 2. If y equals the square root of x, then x equals y squared. We see that the right curve is the line, so that the height is the curve on the right, which is y plus 2, minus the curve on the left, which is y squared in terms of y, because the thickness is delta y. So we would need to express every expression in terms of y. Using shell methods, the volume of a representative shell is 2 pi r, which is the circumference of the shell, times the height times the thickness, but the thickness is delta y in this case. The radius is y. The height is y plus 2 minus y squared, and the thickness is delta y. The total volume is therefore the sum, as I go from 1 to n, of 2 pi y times y plus 2 minus y squared delta y. And as n goes to infinity, we obtain the definite integral, so the volume is 2 pi, the integral from a to b. To obtain the limits of integration, we observe that we only slice this solid from y equals 0 to whatever this y is. But if the intersection of these two curves is at x equals 4, then y equals 4 minus 2, which is 2. And so we would integrate it from y equals 0 to y equals 2. Y squared plus 2y minus y cubed dy. We need to simplify the integrand so that we can find the antiderivative. Using the fundamental theorem of calculus, we can easily use the power rule to find the antiderivative of these. We plugged in 0 and 2 into the antiderivative to obtain 16 pi over 3. This is the exact volume of the solid generated by rotating this bounded region above the x-axis.